Here is a problem from our studies of rotation. In this case, we have a rotating turntable, and it has an original velocity when suddenly an additional mass is added to it, and you are challenged to find the new angular speed of the turntable and the mass. When you have a setup like this, you should recognize that this is a law of conservation of angular momentum problem. The symbol for angular momentum is L, but I don't think you particularly need to know that. But if I set this angular momentum equal to that angular momentum, I'll be able to solve the problem. So any angular momentum, like a linear momentum, let's see, that had something to do with mass times velocity, right? So there's our law of conservation in shorthand for law of conservation of linear momentum. So instead of mass, if I want angular momentum, I need rotational inertia. And instead of linear velocity, I'm going to use angular velocity. So I'm going to set the products equal to each other. So this will be the original rotational inertia, and this is the original rotational velocity. And here we have the final rotational inertia and the final rotational velocity. So a disk like this, a turntable, is really a slice of a cylinder. So if you look at an equation sheet that tells you what your choices are for rotational inertia, you can see here that we have a solid cylinder. That's the same thing as a disk or a hoop. And the equation in that case for its rotational inertia will be 1/2 mr squared. 1/2 mr squared. Because on average, the mass is about halfway out if you take the location of all the points of mass on that turntable. So that means this I is going to be substituted with 1/2 times the mass of the turntable, given to me in the problem is 34 kilograms, times the radius of the turntable, which is 2.1 meters. That's nice that they gave me radius, nice that they gave me meters. I do have to remember to square it. Watch out if they give you a problem with diameter and centimeters. You need to get into the International Standard Unit, and it needs to be the radius. On the right-hand side, I have something a little more complex. I need to take the rotational inertia of the disk plus the rotational inertia of what I'm going to call the particle. In this case, it's a lump of clay that has dropped onto it. So I have to get those two things figured out as the new rotational inertia of the system, and then multiply that times the final rotational velocity. So working on just the right-hand side for a minute, I'm going to go back and put in what I had for the disk, 1/2 times m times r squared for the disk. And I'm going to add to it what I have for a particle. Now, the particle has its mass a full radial distance away from the circle that it's involved with. And if you look at the equation sheet here, it doesn't have a particle. What it has instead is a hoop. So a hollow ring or a hoop or a particle all have an rotational velocity, all have a rotational inertia equal to mr squared. So that's because the full mass is the full radial distance away. So I tend to think of it like a lump of sidewalk chalk. If you go out on your sidewalk with your lump of chalk and you draw a circle, that particle is moving in a circle, right? And so that particle has its mass this whole radial distance away. Well, so does the circle that you drew on the sidewalk. So as long as you have a thin ring or a hoop, your rotational inertia is going to be mr squared. So I need to be careful now and change to the 12 kilograms of mass that's appropriate for this particle or lump of clay, and its radial distance out, which is 1.1 meter. Remember to square that. And that wide expression now, it's almost off the side of the page, is the new rotational inertia. And that's what I'm going to multiply times the rotational velocity that I'm seeking. So when you get your calculators out, you're going to have an 89.49 on this side, and that'll be kilograms times meters squared, because that's what we were working with up here. And that's what we have in the bracket, time the final rotational velocity. Where on the left-hand side, I come up with 577.269, a bigger number because we multiplied it times the rotational velocity right there, which was given in the problem as 7.7 radians per second. So that means my unit over here has radians per second in it, and kilograms, and meters squared. So the units are going to work out beautifully. When you go ahead and divide on your calculator, you should get 6.45 radians per second. So there you have a classical conservation of angular momentum problem.